मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी राजधानी।
My dear students, well, we are going to start the 24th lecture in the series of mechanics of metal forming. As you are aware of, we are discussing the different modeling techniques. Previously, we have discussed the slip line method out of this. But as you remember, during those lectures, I stressed that the very beginning method that was the slab method. So, in this lecture, you would be discussing the slab method and other techniques as well, which are used for modeling metal forming processes, various metal forming processes like upper bound, and then most advanced, that is the numerical methods like finite element method, and then many other types of finite element method in that. So, we are going to start with the slab method here. So, as you know, the modeling techniques, the most fundamental calculations used in metal forming analysis involve a forming load estimate, okay, which is used in selecting the size of the equipment required to form the product, any product. So, the simplest formula that has been used, you are all aware of that the simplest form of the formula becomes capital P, which is load, is equal to capital K, and the stress, that is the sigma bar, you can say, generalized stress, multiplied by the cross sectional area where the load is there. So, you can say the stress, this as a mean flow stress as well of the workpiece material under an idealized state of deformation. And as you know, A is the planar area, you can say, of the workpiece. K, which is given here, is an empirically determined correction factor for a particular forming process. So, it has to be calculated, this constant K. So, this correction factor in fact reflects on the effect of the non-uniformity of deformation and friction between the workpiece and tool. This estimation, that is the value of K, has been improved upon by more elaborated approximate solution technique such as the slab method, the slip line method, the upper bound method, lower bound methods, Hill's general method, and finally the finite element method, FEM. In fact, these methods have been employed to allow for the estimation of not only the forming load but also the material flow pattern and the stress distribution. The first two methods, that is the slab method and the slip line method, solve the field equations in a differential form directly with certain degree of simplification. On the other hand, the other methods solve the field equation in an integral form, which is derived from the associated energy theorems, as you are now aware of this. Except for the FEM, application is generally limited to metal forming processes with simply geometry and idealized materials laws. Okay, so we would be discussing now briefly the some of the classical solution for the slab method. As you know, the slab method is also called as equilibrium method. It is very popular because this method consists basically in isolating a representative volume element in the body of the material undergoing plastic deformation and identifying all the normal and frictional forces acting on this particular element. The behavior of the element is then analyzed by considering the equilibrium of forces acting on it at any instant of deformation. Because of this simplicity, this method of analysis, that is the equilibrium method or slab method, has been used very widely for almost all metal forming processes and is quite useful in estimating forces in processing. This method is only approximate and underestimates the magnitude of the forces involved by virtue of ignoring the effect of redundancy on the one hand and on and of the pattern of flow on the other hand. It is particularly suitable for wire drying and for tube drying, hot and cold rolling of strip and sheet, rotatory piercing and elongation of seamless tubings, for all these applications. To improve the accuracy of calculations, we can modify the value of operating stresses resulting from the integration of equation of equilibrium either by introducing the stress redundancy factor or by modifying the value of the yield stress. So, as has been said, that the slab method is based on the assumption that the deformation of a workpiece can be approximated with the deformation of a series of slabs, and the shape of the slab, that is either flat or cylindrical depending on the problem, does not change in the course of deformation. So, each slab having an infinitesimal thickness is sliced so that it contacts with the tool, whatever tool it is. So, these methods in fact assume that the shear stress due to friction between the workpiece and tool does not affect the stress distribution within the slab, but it is considered in the force equilibrium diagram case. The stress distribution within each slab is in fact simplified further such that the stress component normal to the thickness direction can be varied as a function of the thickness coordinate. The other non-trivial stress component are then related to the stress component normal to the thickness direction according to the yield criteria whatever is being used and the flow rule for a rigid perfectly plastic material. Then the differential equilibrium equation expressed in terms of the stresses and the thickness coordinate is solved with the associated boundary condition of the problem. The slab method therefore has been applied very widely to, as I said just now, for various plane strain or axisymmetric forming problems, including your upsetting, extrusion, drying, rolling, all that things just I told you. So, with this particular background about the slab method, let us take some problem. Let us take this figure 1 where it is shown here a ring compression problem. Usually a ring compression is very popular in metal forming to find the coefficient of friction value between the two interfaces, that is the workpiece material and tool. So let us take this one. So this particular figure 1, if you look at this illustrates a simple example of the slab method which is applied to a ring compression problem. In fact, the ring compression test has been used very widely as a convenient tool to evaluate the friction factor, as I told you. In bulk metal forming industries, the constant shear friction model, which is based on the shear strength of the workpiece, has been preferred to the well known Coulomb friction model, which is basically based on the contact pressure. So if you look at this figure where the inner radius, that is capital Ri, has been shown, and the outer radius, which is shown as the capital Ro, and the height is capital H, initial height of the ring, and this is what is the geometry of the ring is shown. Now consider an infinitesimal element which is depicted in the figure B here, 1b. So the equilibrium equation in the radial direction can be very well written. As I told you, it starts with writing the equilibrium equation. So if you look at this figure B, this is at the top, the mk is your one of the sliding friction, which is the interface here, and then these are the components, say sigma theta, and here, and the sigma r on this side, inner side, and the outer is sigma r plus d sigma r, and this is the what is the dr is the small infinitesimal radius thickness has been taken. So if this slab, that is the ring, is taken out, so one can write down the equilibrium equation, which is now it is shown here. So this equilibrium equation can be written as sigma r multiplied by h r d theta minus summation, that is sigma r plus d sigma r multiplied by capital H, and the area, that is r plus dr multiplied by d theta, plus the second component, that is 2 sigma theta sine d theta by 2 capital H dr, and minus plus 2 mk r d theta dr, and that the summation should be equal to 0. And you can see here from the geometry itself, d sigma r is actually, it can be minus plus 2 alpha k dr, where alpha is the ratio of m by capital H, and it's a constant which represents the coining effect, that is a portion of the total forming load required to overcome friction increases as the height of the ring decreases. That is the coining effect. It is noted that the assumption, which is sigma r is equal to sigma theta holds when the radial component of the velocity u is function of homogeneous degree 1 in r. So one can write that du by dr becomes equal to u by r, which is shown here. R, simply it can be written that the strain r, that is the strain rate in r direction, is equal to the strain rate in theta direction. And by applying the boundary condition, that is at the stress at the radial, that is the sigma r is 0 at when inner one, because the r, when it is r is equal to ri, the stress sigma r is 0, and when r is equal to ro, that is the r there also, this is 0, both case. So, if we take the equation 4 and if it is integrated, so one can write down here. So, that means sigma r it becomes, depending on the situation, whether the radius is less than or equal to neutral radius, or it is greater than or equal to neutral radius, the two cases may arise. So, when it is less than or equal to neutral radius, it is the sigma r is equal to 2 alpha k r minus ri, and it is when it is greater than or equal to radial neutral radius, it is 2 alpha k capital R O minus R. Since the stress must be continuous at your and the location of the neutral point is determined by, one can find out the neutral point as half of RO plus RI as usual. So, then one can find out the yield stress of the material, that is what is the sigma bar, that is also called as the generalized stress, and that is simply the sigma z minus sigma r mod. So, that is the positive side of this, and that is what is the yield y, capital Y, where the, and therefore sigma z is in fact capital Y plus sigma r, and therefore now one can write down the load required, capital P is the integral, the two integral that correspond to the summation. That means it is the integral from inner radius to the neutral radius. So, the first integral from inner radius Ri to the neutral radius Rn multiplied by sigma z 2 pi r dr, plus second one from neutral radius to the outer radius, that is the ring which is there. So, that is the integral over Rn to R0 and of the sigma z 2 pi r dr, that is how the, and that should be equal to, if I write it capital K slab as the correction factor. So, that becomes K slab sigma bar, that is the generalized stress as shown here in equation 7 multiplied by cross sectional area A. So, the K slab in fact is the correction factor or normalized forming load, and therefore you can, if you extend it, one can see that correction factor K slab becomes equal to 1 plus 1 by 2 root 3 m by h multiplied by Ro minus Ri, and this is what has been shown here in equation 10. So, this is what is the very simple example of the ring test using slab method. As you know, this method, slab method, entails a force balance on a slab of the metal of differential thickness, as you have seen, and this produces a differential equation as you have seen with the variations where the variations are considered in one direction only, and then you apply the boundary condition, and then you applied the integration of the equation, and you got the solution. So, this is what is the way, but please note that there are certain assumptions in most of the slab method. There are few assumptions. So, generally assumption 1 is that the friction does not influence the orientation of the principal axis. Okay. So, it is to be noted, and within the deformation zone the x, y, z are fixed as the principal axis within the deformation zone. Secondly, the plane section remain plane. This is very important, and that is why the plane strain conditions prevail. Thus, the deformation is homogeneous in regard to the determination of the induced strain. And thirdly, which is very popular and important, the principal stresses do not vary on the z plane. So if you look at this figure here, if you this is an example where figure number 2, where a seed drying is now taken up. Let us take the seed drying problem and let us solve it with the help of slab method again. So whatever assumptions, these three assumptions, it prevails here also in this case. So if you look at this figure, this is the a slab and it is being drawn within these drying dies. So look at, this is the entry thickness is T0 and Tf is the final thickness after, and you look at, and in between there is a slab, a small slab is taken over here in between when it passes through the die, and this is what is the XYZ coordinate system is there. So this is and therefore at the end we are putting the neutral axis. So at the end, that is the 0, 0 point. So if we look at this problem which is shown here in figure 2, so I can now take the slab which is formed in between, and this slab is shown here. So this is what the slab, and you will see on the right side, and this is what is the 0, 0 point. So XYZ, that is the neutral new coordinate system, and x is start from this point. So x, and this is the dx is the thickness of the slab is taken, and then there is a sigma that is the stress, that is the stress in this direction, okay, and the stress plus infinitesimal is on the other side. On the top where there is a contact with the tool, it is the nu p. Nu is the coefficient of friction if it is, and p is the pressure which is applied. So it is on both sides it is applied. So now you see all the forces which is acting on this small element is shown. So this is the balance of the force in the x axis. So that is how the sigma x and sigma x plus d sigma x. And on the right side this figure is shown where the balance of the forces in z direction has been shown. Here if you see the z direction, this is what is has been shown. So this is the angle alpha, and in z direction this is sigma z dx, and you see the length, this is the angle in between dx and dz, and this is what is the component of nu p, that is nu p sin alpha, and this is what is nu p cos alpha d alpha, and these are the forces which is acting, the frictional forces acting on the this angle alpha, okay. So if you look at this equilibrium balance of the forces on the slab, this particular slab, and let us start with the plane strain drying. So the drying stress can be defined as, which is shown here in equation 1 of this problem. So that is the force capital F divided by W Tf is equal to sigma d, alright. And if you apply the incompressibility condition, that is the, what is the incompressibility equation? That is the strain in all the directions, sum of the strain is equal to 0. That means epsilon x, epsilon y and epsilon z summation is 0. And in case of plane strain condition, what will happen? Because for the plane strain sigma y is 0, and therefore this the incompressibility equation will result into, that is epsilon x is equal to minus sigma epsilon z, and then one can define the homogeneous strain, that is if it is defined as epsilon h as the homogeneous strain. So keeping into mind with this slab that there is a dh by 2, this is the height, dh by 2, the difference here. So keeping in this mind, then one can write down the homogeneous strain, that is the epsilon h, is that is at the exit point, and that is how it is written in equation 5 as epsilon x at the exit point, that is the homogeneous strain, and that is again equal to minus epsilon z, which is at the exit, and that is nothing but your engineering strain, that is ln T0 by Tf. Alright. So, if you take the balance of all the forces in z direction, that is the summation Fz is equal to 0 in the left free body diagram, which is shown here. So, what one can write down the equation, the equilibrium equation as sigma z dx plus p ds cos alpha is equal to nu p ds sin alpha, where the cos alpha one can see from the geometry, it is equal to dx by ds, and sigma z is nothing but therefore minus p plus nu p tan alpha, and that is again equal to minus p multiplied by 1 minus nu tan alpha, and generally nu tan alpha is quite less than 1, and therefore one can say that sigma z is approximately equal to minus p. So, indicating that this minus sign shows that it is compressive in nature, sigma z is compressive. So, using the flow rule now for that is incremental strain in y direction is 0. So, we have the deviatoric part of the stress in y direction is 0, or finally if you use this equation 7, that is sigma z is approximately equal to minus p, the deviatoric stress can be now written, that is the deviatoric stress sigma y is nothing but sigma x plus sigma z by 2, and that is further can be equated with the help of equation 7 as sigma x minus p by 2, and this is what has been shown in equation 8. So, in terms of principal stresses, since sigma z is obviously tensile, then one can say that sigma 1 is sigma z, sigma 2 is sigma z minus p by 2, and sigma 3 becomes minus p. So, if you substitute in the von Mises, let us apply the von Mises yield criteria. So, it will give the following relation between the stress component to the initial and the sustained plastic deformation under plane strain condition, and this is what has been shown here in equation 10. So, it becomes that sigma z plus p is equal to 2 capital Y by root 3 yield. Capital Y is the yield strength of the material, or P is the P becomes 2y by root 3 minus sigma z. This equation, that is which is shown in 10, equation 10, is a valid in any location inside the deformation zone, and but we assume a non-hardening material because yield is y is constant. So, the strain hardening is not considered here. Please note, in all the slab method we never consider the strain hardening, and then the equilibrium equation of the forces in x direction can be written, and this is what has been shown here in equation 11. So, that becomes sigma z wt plus sigma z plus d sigma z multiplied by t plus dt w plus 2 p ds w sin alpha plus nu p ds w cos alpha, and this is all summation is equal to 0. And after neglecting higher terms like d sigma z and dt, if we multiplication if we neglect expanding this equation 11, So one can get the very simplified equation as 12, that is sigma z dt plus t d sigma z plus 2 nu p ds cos alpha. Please remember, do not confuse m and nu. M is also in most of the literature is used for as the coefficient of friction. Nu is also used as the coefficient of friction in other. So let us use simultaneously, and that does not matter because previously we used m. So the students should not confuse with this. So and then the third term is the 2 ds sin alpha p, this is 0, and if you use, because dt by 2 is your ds from the geometry, ds by sin ds multiplied by sin alpha. So one can finally write that t d sigma z plus sigma z plus p multiplied by 1 plus nu cos alpha and multiplied by dt is equal to 0. And let us assume that capital B, let us define a factor capital B which is equal to nu cos alpha, we can say. Then this equation number 13 can be written, that is the equilibrium equation, is simplified as T d sigma x z plus sigma z plus p 1 plus capital B and dt is equal to 0. So substituting the value of p from the equation number 10 which we have got in this equation, one can this equation 16 which is there. So we get a equation, a kind of differential equation, that is d sigma z divided by denominator side is capital B sigma z minus 2y under root 3 1 plus b, and that is what is equal to on the right side as dt by t. So the solution is the solution to equation number 16 is based on certain assumption, as I told you. So the assumption is that an average a constant value, the coefficient of friction nu is average and it is constant in full contact of the region. And also the material does not work harden, as I told you, and therefore a mean value of the yield stress strength which is adequately is sufficient to describe any work hardening effect. In either case, capital Y is treated as the constant, and the semi die angle, the alpha, as I told, is also constant, that is not going to change. So under these three conditions, if we solve the equation, differential equation 16, and we can start with direct integration using the boundary condition as sigma z is 0 when t is equal to t0 and sigma z is sigma d when t is equal to tf, that is the final thickness. One can get the sigma d, that is the stress, drying stress, sigma d is equal to the numerator, on the numerator it is 2 yield or 2y by root 3 1 plus b divided by capital B, and on the other factor is 1 minus t t e, that is the entry, divided by t o and raised to the power capital H. So if you apply the homogeneous strain, then the same equation 17 can be written as, which is shown here in equation 18. So you please note that the capital B, it tends to 0, that means there is no friction, right? So using the Taylor series, if we use the Taylor series and we can expand the exponential term which is shown here in equation 18, one can see. So if it is used, then one can write down that sigma d multiplied divided by 2y under root 3 becomes equal to 1 plus b divided by b and multiplied by 1 minus exponential minus the remaining part, and that is equal to 1 plus b divided by b multiplied by 1 minus and then 1 minus b homogeneous strain plus capital B square and so on. So, if you apply the Taylor's equation, this has been shown here in equation 19. So, if B tends to 0, so that case what will happen when it is there is no friction, that is the frictionless drying, then in that case it is simply sigma d by 2y under root 3 and it is equal to homogeneous strain, that is epsilon h, and that is simply equal to ln T0 by Tf. So, this is what is the answer, and this is also provided by the ideal work method if you use. So, from this example it can be seen and it can be realized that the slab method analysis simplify it simply extends the information provided by the ideal work method to include the frictional effects as well. So, that is a very effective one. Let us take one simple numerical example based on this. So, let us take an example where a sheet of metal having an, based on this previous derivation, the sheet of metal having an initial thickness say 0.1 inch and the width as 12 inch and it is being drawn through straight sided dies which has got an included angle as 30 degree. If the average of the yield stress is, that is capital Y, is taken as 30 multiplied by root 3 KSI, and an average value of coefficient of friction, that is nu, it is taken as 0.08 in the cold condition, and please note that these analysis nowhere includes temperature. So, it is mostly the cold condition forming. So, let us, under this condition, let us calculate the force needed to complete this operation and let the reduction is 10%. So, how to start? So, if you use the previous equations, that the slab drying, so from the data which is given here, what we apply? We see that capital B, which is equal to nu cos alpha, where the alpha is the semi die angle, and that's what's the, it is 30. So, semi die angle becomes 30 by 2, that is 15 degrees. So, one can find out very simply capital B. So, let us try. So, what is the value of B? Yes, Mr. Rohit? Yeah. So, capital B comes out to be 0.08 cot 15, and that is approximately 0.30. Okay. Now, what to proceed? So, one can now find out the homogeneous strain, that is epsilon h. So, that is nothing but ln 1 by 1 minus r. So, the r is nothing, you can see r, it is already, you can see it is 0.1. So, this epsilon h homogeneous strain becomes 0.105 because r is you can calculate from the geometry, previous geometry, and that is simply T0 minus Tf by T0. That is how the r value is 0.1 inserted here. So, now if you put this data into the drying stress required, so drying stress becomes 2 capital Y root 3 multiplied by 1 plus B divided by B and multiplied by this factor, that is 1 minus exponential minus capital B and homogeneous is strain that you have calculated. So, if you substitute this, all this and calculate the drying stress for this particular case. For drying at 10% reduction, one can calculate as 8.08 KSI. So that is how one can, a very simple problem. So once the drying stress has been calculated, and if you multiply it by the area, one can find out the drying load, drying force. That would be simply sigma D multiplied by W multiplied by TF, and that comes out to be 8730 pound feet. Okay, so this case we consider the drying of a slab. One can also apply the drying wire drying as well. So you know, wire dryings are rods having input as a rod. So if you apply the slab method to the rod drying, the principal stresses would be, can you see the principal stresses, that is sigma 1, sigma 2 and sigma 3 would be what? So sigma 1 would be equal to sigma z, sigma 2 would be equal to sigma 3, and that is equal to simply minus p, because it is a rod now. So z is in fact the main axis, and the direction 2 and 3 are the hoop and radial directions. So if you consider this, and if you substitute of the above equation in the von Mises criteria, if it is used, so one can find out the a equation, that is the stress component to initiate the plastic deformation. So one can write down that sigma z plus p is equal to capital Y, or simply p is capital Y minus sigma z. So that's how it is enough to sustain the plastic deformation. And for a wire or rod of circular cross section, then the basic governing equation one can write here. So this is, one can write as d sigma z divided by capital B sigma z minus capital Y 1 plus B. Capital B is same as we have taken in the slab drawing. So that becomes equal to 2 d capital D by capital D. So capital D is the diameter of the rod, and where we define as 2 d capital by D as minus d epsilon z. So one can now write down the integral, and this is what has been shown here, if you recall, in equation number 30. So if you integrate on the left and right side from the equation 29, one can get the sigma d for the wire drawing as this one, 31. So that is the y multiplied by 1 plus b divided by b, and multiplied by 1 minus exponential capital B and homogeneous strain epsilon h. So epsilon h is, and that is the homogeneous strain, is defined as 2 ln d O by df, because the initial do is initial diameter, and after reduction df is the final one. So that's how the homogeneous strain is defined. So you look at this figure, this is what the figure number 3 relating the rod drawing. So you look at here the how you take the slab, small slab here, and you see the forces, that is the sigma z, and now wire drawing means it's a pulling force is applied. So this is what the z is taken as 0, x y z coordinate system at this end, z and dz is the thickness of the slab, and again the p, nu p, and all those things analysis. So this is what we can calculate the sigma d as shown in 31, and it is quite similar to the slab drying. It's okay. So it is so simply, but we will see why the slab method did not continue. It's a approximate, it's an approximation. We will see. So let us once again take another plane strain extrusion also. So let us just write, you can apply this slab method concept to the plane strain extrusion, and let us write the equations only for using the plane strain, similar to plane strain drying. So look at this figure 4, where axisymmetric extrusion is taken. So you know that in extrusion you push from one side, there is a die, the billet is kept and it is being pushed, and through die it comes out. So there is the pushing force, and in the wire drying it has been was a pulling force. So if you look at this figure, this is what the container, this is the what the slab is taken. This is what the slab of thickness dx is taken, and the final diameter is capital DF, final area is capital AF, and this is what the exit diameter and the cross sectional area. And likewise here your DO and AO area, initial billet one can consider. So this is what's the die, right? So based on this one can write this equation 33. So that is what's the pressure at the exit is 2y root 3 1 plus b by b multiplied by minus 1 plus exponential plus b epsilon h, homogeneous strain. And for axisymmetric extrusion, therefore it becomes, that is your capital Y 1 plus b b minus 1 exponential plus b, and that's the equation 34. And you can, I am not going into details because it is quite similar as the wire drying cases has been there. So I am just writing the direct formula here. So anybody can try and we will get the same equation. So the only thing is to be noted that the equation is for a non-hardening material, and in case of a hardening material one can use the above equation again as an approximation, and just you take the value of y to be the mean yield stress over the range of the strain induced by the shape change. One can do like that. Secondly, it should be noted that these analyses, because which unrealistic at high die angle and low reductions. So assuming that P is a principal stress is reasonably only if alpha is very small, the die angle, and friction is low, otherwise it will not be true. So under this situation only it is considered. And you know that all analysis, that is the slab analysis, do not account for redundant, that is non-homogeneous deformation. Nowhere you have seen. So the slab analysis, it never takes redundant deformation, which is, we call it as a non-homogeneous. So that's the weakness, and the other method will try to overcome this. So let me again recall the assumptions that for the slab method, that the deforming material is isotropic and it is incompressible. Secondly, the elastic deformation of the deforming material and the tool are neglected. This is also to be assumed. The inertial forces are very small and therefore it is again neglected. The frictional shear stress is constant at the die material interface. It is always constant, it do not change during the process, and the material flow according to von Mises criteria. We consider it the von Mises yield criteria. The flow stress and the temperatures are constant within the analyzed portion of the deforming material. So these points are always there in slab method. So we can further take some more example, and so under these assumptions, let us take a open die forging problem. So you know, in open die forging that and you plane strain, so it becomes a similar to plane strain upsetting. So we can take a slab of infinitesimal thickness and which is perpendicular to the direction of the metal flow, and this is what is being shown here, shown in figure. So this is what is the slab is taken of, this is the direction x and this is direction z where the sigma z is stress, and this slab is taken. So r direction is here in minus x direction, and this is what the stress is shown. So this is what the equilibrium of forces in plane strain homogeneous upsetting is shown here. So with respect to this particular figure, if you recall, one can write down the summation, the equilibrium equation, that is the summation of forces in the x direction, and that would be equal to 0. So what we can write down, that the summation over x direction is equal to what? Sigma x multiplied by h minus sigma x plus d sigma x multiplied by h and minus 2 tau dx. So tau is shear stress, or simply one can write down that d sigma x is equal to 2 tau dx by h, and that is the minus. So if you integrate, one can find out that sigma x is equal to minus 2 tau by h x plus capital C. C is a constant. So from, if you apply the flow rule that is under the plane strain, so it becomes sigma x becomes equal to minus 2 tau by h x plus C plus 2 by root 3 sigma mod. That is what is the. So this particular, as I said, the constant C is determined from the boundary condition, like at x is equal to half, that is the mid where the sigma x is 0, and therefore one can write down that the sigma x is mod 2 by root 3 sigma, and that is what has been added. So the sigma x finally it becomes as minus 2 by tau 2 tau by h multiplied by L by 2 minus x multiplied by 2 by root 3 sigma. So this equation illustrates that the vertical stress which linearly increases from the edge which is at x is equal to half L by 2 of the which has been shown here in figure, and it is towards the center, it becomes 0, x at x is equal to 0. So the frictional shear stress which is tau here is equal to what? That's the frictional shear stress tau. So that becomes m multiplied by generalized stress by root 3. Generalized stress, as you recall back, we have represented it as a sigma bar. So the integration of the equation over the entire width from, that is the length L of the strip of unit width which is perpendicular to the plane. So the offsetting load per unit depth can be calculated, and that is what has been there. That is, this load is 2 sigma by root 3 multiplied by 1 plus ml for h. That's how the simplified load for the upsetting. Alright. For axisymmetric case, this has been for situation where you have the plane strain. That for the axisymmetric, the flow rule or axisymmetric deformation can be obtained by using a derivation similar to the plane strain deformation just now we did. So equilibrium forces in the r direction can be calculated as, you can refer the Hoffman 1953 reference that we have already listed. So in that axisymmetric case, the summation over radial direction of the forces will become like sigma r d theta rh minus sigma r plus d sigma r multiplied by r plus dr multiplied by h d theta plus 2 sigma theta sine d theta by 2 h dr minus 2 tau r d theta dr. So if we simplify and introduce the approximate boundary conditions, that can be found out as sigma z, and then sigma z is in fact it is 2 tau by h multiplied by small r multiplied by capital R multiplied by sigma. This equation says that the stress increases linearly from the edge towards the center, and therefore the upsetting load in axisymmetric can now be written as capital L as sigma pi r square multiplied by 1 plus 2m capital R 2h divided by 2h by root 3, and this is the what's the geometry of the slab for the radial. So the forces equilibrium in the axisymmetric homogeneous upsetting is shown here. So this is what's the ring is R, dr, h, and this is what the 3D case and which has been shown. This is the stress theta, and this is in the radial direction. So so because when the modeling concept is started, so the slab method was very useful in this way. There are other methods of modeling, as I told you, because the inherent weakness of the slab method is that you cannot apply it for the 3-dimensional case, and that too when the geometry of the workpiece are forming becomes very complicated. So the upper bound technique is another one which is very popular, and where the overall deformation zone is divided into a number of smaller zones within which the velocity of a particle is continuous. The particle velocities in adjacent zones may be different, however, at the boundaries between the zones or between a zone and the die surface. So all movement therefore be such that the discontinuities in velocities occur only in tangential direction. So in this situation, the upper bound, how can be very simplified manner is used to calculate the power consumed in the operation. So it can be simply said that capital P, that is the power, becomes Pi plus P1 plus P2 plus P3, where one can say the P1 is the ideal power for the deformation, P2 is the power consumed in shearing the material along the velocity discontinuities, P3 is the power required in overcoming the frictional forces at the die workpiece interfaces. So that's the simplest we actually these things comes into limit analysis. So limit analysis deals with two types of techniques, one as the upper bound and lower, and another is the lower bound. The upper bound technique is concerned to us in metal forming because it deals with the plastic deformation, whereas the lower bound concerns with the within elastic region, and that is more concerned with the structural engineering uh, guys. So then there are other method of like viscoplasticity, and then the numerical methods wherein finite element method and all those things comes. So we would be discussing in the next lecture the limit analysis, that is the upper bound and lower bound, and we will see in detail and with many examples. So that may continue up to 4 lectures, maybe that lecture 25, 26, 27 and 28 will continue with the upper bound and lower bound details, and hopefully this will help you all, and I understand that you would be, you can, maybe that there are certain uh, objective problems as well on the web, you can check it and solve to improve your understanding. So I thank you once again, all of you, for keeping patience, and but please, once again, please do not forget to give your feedback. So thank you.